Right now, beneath the Atlantic, a current wider than the Amazon River is starting to falter. It carries more warm water than every river on Earth combined. It is the reason Europe stays warm, and the reason your winters feel the way they do. We treat this ocean like it will always behave the same way. But the Atlantic is entering a new phase, and it raises one serious question for America. You will ride the warm river that feeds a continent. You will watch a flood break this same ocean 12,000 years ago. You will see a coast where the sea suddenly climbs, and a future where the Atlantic itself begins to close. If wonder like this keeps you curious, take a second to like and subscribe. It helps more than you know. So take a breath. We are going in, stand on a beach and watch the Atlantic roll in, and it feels like the most permanent thing on the planet. The waves have looked the same your whole life. They looked the same to your grandparents. They will look the same tomorrow. That is the trick this ocean plays on us. The surface never lets on what the water beneath it is doing. Down in the dark, far below the waves, a giant current is moving. It runs the length of the whole ocean, from the warm waters near the equator all the way up toward the cold seas near the Arctic. You cannot see it from a boat. You cannot feel it from shore. This current is one of the main reasons the world you live in feels the way it does. It decides how warm your winters are. It shapes where the rain falls and where the storms go. It helps set the level of the sea against the streets of every city on the East Coast. For thousands of years, it has done its job quietly and stayed strong. Something has changed. Over the last few decades, scientists watching this current have started to notice small warning signs. The water is behaving in ways it should not. A patch of the ocean that should be warming is cooling instead. Numbers that held steady for centuries have started to drift. A growing group of researchers now believe this current is weaker than it has been in more than 1,000 years. Here is the part that matters for you. If this current keeps slowing, the change would not stay out at sea. It would climb onto land. It would show up in the price of food, in the height of the tide, in the cold of a winter, in the path of a hurricane. That is why the quiet shift in the Atlantic has turned into one serious question for America. Is the engine that steadies our climate starting to break down? This is the strange thing about oceans. They give no warning letter. They shift in silence year after year, until one day the change grows too big to miss. By the time everyone agrees, turning it back can be almost impossible. Scientists do not all agree yet, and that honesty matters. Some are certain the slowdown has already begun. Others say the ocean is too big and too wild to be sure this soon. What almost none of them will tell you is that nothing is happening. The Atlantic is entering a new phase. The only real argument is how fast. To understand what could break, you first have to understand what this current actually is. It has a boring name and a wild personality. It moves more water than every river on Earth put together, and it does that every single second of every single day. It runs warm enough to feel like bath water near Florida, and cold enough to freeze near Greenland. People have known about the warm, fast part of it for hundreds of years. Sailors rode it. Pirates hid in it. Explorers raced across it. They gave it a simple name that stuck. That warm river in the sea is where our journey begins. There is a river inside the ocean, and it never touches a bank. Picture the water off the coast of Florida. It looks like ordinary sea. But part of it is moving north in a tight, fast band, warm and blue and powerful. Sailors named it the Gulf Stream because it starts near the Gulf of Mexico. It hugs the American coast, sweeps past the Carolinas, then bends out into the open Atlantic and heads for Europe. Now think about how much water it carries. Every river you have ever seen, the Mississippi, the Amazon, all of them, added together, move a certain amount of water. The Gulf Stream carries many times more than that. If you gathered up every river on the entire planet and poured them into one channel, this ocean current would still move more water than all of them combined. It is fast, too. In its strongest stretches, the water races along at close to 5 miles an hour. That may not sound like much until you remember this is the open ocean. Ships heading south learn to steer around it, because pushing against that flow wastes time and fuel. Ships heading north climb aboard it and let it carry them, like stepping onto a moving walkway at an airport that stretches for thousands of miles. The Gulf Stream is about 60 miles wide in places and runs deep beneath the surface. From above, it would look like a warm blue highway drawn across a colder sea. Satellites can spot it by temperature alone, because the water inside it can be many degrees warmer than the water right beside it. Here is the mystery that made this current famous. All that warm water is coming from the tropics, where the sun beats down hardest. The Gulf Stream is carrying that heat north, away from the equator, toward the cold top of the world. It is like a delivery truck loaded with warmth, driving thousands of miles to drop it off somewhere far away. The question is, where does the heat go? Because heat does not vanish. As this warm river travels north, it slowly gives its warmth up to the air above it. Winds pick up that warmth and carry it over land. By the time the water reaches the seas near Iceland and Norway, most of its heat is gone, spent into the sky. That handoff from ocean to air to land is the whole reason this current matters to people. The Gulf Stream is a small part of a much larger machine. On its own, it is already one of the strongest flows of water in the world. Yet it is only the warm, visible beginning of something bigger, a loop that reaches down into the deep and stretches across the entire planet. And the place where the Gulf Stream drops off its heat is a place that should be freezing. It sits at the same distance from the North Pole as parts of Canada that stay locked in ice for months. Somehow, the cities there stay green and mild through winter. That warmth does not come from the sun. It comes from this current, arriving by water from thousands of miles away. Which raises a strange question. What would happen to those places if the delivery ever stopped? Two cities can sit at the exact same distance from the North Pole and live in completely different worlds. Take London, in England. Now find the spot in Canada that sits at the same height on the map, the same latitude. That part of Canada spends its winters buried in snow and locked in deep cold. London, at the same line, stays green. Its winters are grey and damp and mild. People there rarely see the kind of freeze that Canada takes for granted. The difference is the current we just met. All that warm water the Gulf Stream drags north keeps handing its heat to the winds that blow across Europe. Those winds arrive soft and warm instead of harsh and frozen. Western Europe gets to live like a place much farther south than it really is. Now try to picture the size of that gift. The heat this ocean current delivers to the north is enormous. If you tried to match it with machines, you would need something close to 1 million power plants running at full blast, all day, every day, forever. The ocean does it for free, with no fuel and no off switch, simply by moving warm water from one place to another. Because of that heat, much of Europe stays as much as 18 degrees warmer in winter than it would be if the current disappeared. That is the gap between a cold day you can walk through in a jacket and a brutal freeze that shuts a country down. Think about what depends on that warmth. Farms across France, Britain, Ireland, and beyond are built around mild winters and long growing seasons. Cities are built without the heavy defences that truly frozen places need. Millions of people live their whole lives inside a climate that an ocean current quietly pays for. Now for the uneasy part. This warmth is borrowed, not owned. It arrives by ocean, on time, load after load, only as long as the current keeps flowing at full strength. Slow the delivery, and the warmth that keeps Europe green starts to fade. The farther north you go, the more the cold would bite. Britain and the countries near it would feel it worst, because they sit right where the warm water gives up the most of its heat. Scientists are confident about this basic picture. The link between the current and Europe's mild weather is well tested and widely agreed on. What they argue about is how fast the current might change and how hard the cooling would hit. That part is still being worked out. So far we have followed the warm water on the easy half of its trip, the sunny surface journey north. That is the part people have known about for centuries, the part sailors could see and feel. But warm water heading north cannot be the whole story. If the ocean only pushed water in one direction, it would pile up against the top of the world and stop. For the current to keep running, the water has to come back somehow. It has to complete a loop. The return trip is the strangest part of all. It happens in the cold and the dark, thousands of feet below the surface, where no sunlight ever reaches. To find it, we have to follow the warm water all the way to Greenland and watch what happens when it finally runs out of heat. At the top of the Atlantic near Greenland, the ocean does something that sounds impossible. It falls. Follow the warm water on its long trip north. Mile after mile, it hands its heat to the sky. By the time it reaches the cold seas around Greenland and Iceland, it has changed. It is no longer the warm blue river that left Florida. It is chilled, grey, and heavy. That last word is the key. Heavy. Cold water is denser than warm water. Salty water is denser than fresh water. The water arriving up north is both cold and salty, so it becomes some of the heaviest water in the entire ocean. And heavy water does what heavy things always do. It sinks. Picture dropping a stone into a pond. It does not float or drift. It goes straight down. Up near Greenland, whole sheets of surface water do the same thing, all at once, across a huge area. The water grows so dense that it plunges off the top of the ocean and pours down into the deep more than a mile straight down, into the black cold at the bottom of the sea. This sinking is the real engine of the whole system. The warm surface current gets most of the attention, but it is this quiet, invisible plunge near Greenland that pulls everything along. As the heavy water drops, it leaves an empty space behind it at the surface. More warm water rushes north to fill that space. That new water then cools, grows heavy, and sinks in its turn. The sinking is like the drain at the bottom of a giant bathtub. As long as the drain keeps pulling water down, fresh water keeps flowing in from the other side of the tub to replace it. Stop the drain, and the whole flow across the tub slows to a crawl. That is why scientists watch the seas near Greenland so closely. This is where the machine either keeps running or begins to stall. The strength of the entire current, all the heat it carries to Europe, all the effects it has on America, depends on how much water sinks here, and how fast. Now here is the surprising number. The amount of water that pours down into the deep in this region is staggering. Every second, an enormous volume drops out of sight and begins a new journey. It is one of the largest waterfalls on Earth, and almost no one has ever heard of it, because it happens underwater where no eye can see it. Once that water reaches the deep, it does not stay put. It starts moving again, this time in the opposite direction. Cold and dense, it begins a slow crawl back south along the ocean floor, thousands of feet beneath the warm current still rushing north above it. So, the Atlantic is running two currents stacked on top of each other. Warm water flowing north near the surface, cold water flowing south in the deep. One feeds the other in an endless loop. That loop is the heart of everything. It is bigger than the Gulf Stream, bigger than the Atlantic itself. It reaches into every ocean on the planet and takes centuries to complete a single lap. To see the full shape of it, we have to zoom out, far out, until the whole world fits in view. Zoom out until the entire planet spins below you and the ocean stops looking like water. It looks like a machine. We have watched warm water travel north near the surface. We have watched it sink near Greenland and turn cold. Now follow that cold water on the bottom of the sea as it creeps south, thousands of feet down, in the dark. It does not stop at the equator. It keeps going, all the way down past the coast of South America, all the way to the freezing waters that ring Antarctica. There it mixes, gets pushed around, and joins even larger deep currents. Some of that water eventually rises again in the far Pacific and Indian Oceans, warms in the sun, and begins the long trip back toward the Atlantic to start over. This is one connected loop wrapped around the whole world. Warm water riding the surface, cold water sliding through the deep. Every ocean linked to every other ocean by the same slow river. Scientists call it the Great Ocean Conveyor because it works like a conveyor belt in a factory, carrying heat and salt from one end of the planet to the other and back. Here is the number that stops people cold. A single drop of water can take around 1,000 years to finish one full lap of this loop. Water sinking near Greenland today might not see sunlight again for 10 centuries. The last time some of the deep water down there touched the surface, nights were riding across Europe. That slowness is exactly why this matters so much. The conveyor is huge, heavy and unhurried. Machines like that are steady, and they resist change. But machines like that are also almost impossible to restart once they truly stop. A tiny paper boat you can flip back over in a second. An ocean liner that loses power drifts for miles before anyone can turn it around. For thousands of years, this conveyor has run at a strong and steady pace. It carried heat north on schedule. It kept Europe warm and the American coast in balance. It moved nutrients that feed the sea and pulled carbon down into the deep where it could do no harm. The whole climate we call normal was built on top of a conveyor that behaved itself. That is why the warning signs are so unsettling. This machine is not supposed to wobble. It is supposed to be the steady thing everything else leans on. When the steady thing starts to shift, everything built on top of it shifts too. Scientists are sure the conveyor exists and sure it shapes the climate. Those facts are rock solid, measured, and agreed on. The debate is about its health right now, today, and about how close it might be to a serious change. So they went looking for its pulse. If this thing is weakening, it should leave clues. A slowing conveyor should carry less heat. Less heat should show up as cooler water somewhere. A giant machine winding down should leave a mark you can find if you know where to look. They found a mark. It sits in the North Atlantic, south of Greenland, right where the conveyor is strongest, and it is the wrong colour. In a world growing warmer almost everywhere, this one patch of ocean is turning cold. There is a spot in the ocean that refuses to warm up, and it has scientists worried. Picture a map of the whole planet coloured by temperature. Red where the world is heating up, blue where it is cooling down. Over the last 100 years, that map has turned mostly red. Land, sea, air, almost everywhere is getting warmer. The map looks like a slow sunrise spreading across the globe. Almost everywhere, south of Greenland, right in the middle of all that red, sits a stubborn blob of blue. One patch of the North Atlantic has been cooling while the rest of the world heats up. Scientists have nicknamed it the cold blob, and sometimes the warming hole, because it is a gap in the warming that covers everything around it. At first, this made no sense. Greenhouse gases are trapping heat all over the planet, so why would one chunk of an ocean, in the middle of a warming world, go the other way and get colder? It is like turning up the heat in every room of a house, then finding one room that keeps getting chillier no matter what you do. For years, the cold blob was a puzzle. Now a growing number of scientists think they understand it, and the answer points straight back to our conveyor. Remember what the conveyor does. It hauls warm water north into this exact part of the ocean. That heat is what should be keeping this patch warm, like everywhere else. If the conveyor is slowing down, it would be delivering less warm water to this spot. Less warm water arriving means the patch cools off, even as the rest of the world bakes. The cold blob may be a fingerprint, a sign, sitting right on the surface, that the great current underneath is losing strength. One recent study looked at more than 100 years of temperature records and found that only one explanation fit the pattern well: a conveyor that is weakening. That is a scary idea, so it deserves honesty. Not every scientist agrees the cold blob proves the conveyor is slowing. The ocean is messy, and there are other things that can cool a patch of water for a while. This is a strong clue, and a worrying one, but it is a clue, not a courtroom confession. Still, the location is hard to ignore. Of all the places on Earth that could turn cold, this cold spot showed up exactly where the conveyor sinks and turns. That is like your car losing power, and the warning light appearing right over the engine, not somewhere random. There is one more reason the cold blob matters. It might not just be a symptom, it might feed the problem. Colder water at the surface can change the winds and the weather above it, and some of those changes could push the conveyor to slow even more. A weakening that helps cause more weakening is a dangerous kind of loop. To understand why a little cooling and a little melting could tip a giant ocean machine, we need to look closer at the engine itself. We know the conveyor runs on heavy water sinking near Greenland. The real question is what makes that water heavy enough to sink in the first place, and what could make it stop. The whole conveyor runs on a single trick, and it is easier to break than you would think. We already know the water near Greenland sinks because it is heavy. Now here is what actually makes it heavy. Two things: cold and salt. Cold water is denser than warm water. You can almost feel this. Warm water rises, cold water settles. That is why the top of a lake in summer feels warm while your feet find cold water below. Salt does the same job in a different way. Salty water weighs more than fresh water. Add salt to a glass of water and the water grows heavier, drop for drop. Sailors know this. It is easier to float in the salty ocean than in a freshwater pool. Up near Greenland, the water arriving from the south is both cold and salty. Cold from its long trip north. Salty because warm tropical water leaves a lot of its salt behind as it travels. Put those two together and you get water heavy enough to plunge more than a mile into the deep. That plunge is the engine of the entire conveyor. Now picture the opposite. What happens if the water up there stops being so heavy? If the water gets warmer, it grows lighter, and lighter water does not want to sink. If the water gets fresher, less salty, it also grows lighter, and again it resists sinking. Warm it up or water it down, and the same thing happens. The plunge weakens. The engine loses power. Think of it like a diver wearing a weight belt. With the belt on, the diver sinks fast and easily. Loosen the belt, drop the weights, and the diver floats right back up to the surface. Salt and cold are the ocean's weight belt near Greenland. Take them away, and the water that should sink stays up top instead. Here is why that is more than a science lesson. When the water stops sinking, the whole conveyor starts to stall. The plunge is the drain that pulls everything along. Weaken the drain, and warm water stops rushing north to replace it. Less heat reaches Europe. The cold blob grows. The current we have been following loses its strength. For thousands of years the balance held. The water arriving up north stayed cold enough and salty enough to keep sinking load after load, century after century. The weight belt stayed on. The engine kept running. That balance is what is now at risk. The planet is warming, which warms the water. And something else is happening at the same time. Something that is pouring fresh water straight into the exact spot where the conveyor needs it to stay salty. That fresh water is the real threat. A little extra warmth is bad enough. A flood of fresh water, right where the ocean sinks, is the kind of thing that has broken this conveyor before, and the source of that fresh water is impossible to miss. It is the largest island on the planet, and it is covered in a sheet of ice almost 2 miles thick. That ice is melting. Every summer, more of it turns to water and runs into the sea, and it is running into the North Atlantic at the worst possible place. Greenland is losing its ice, and the water has to go somewhere. From above, Greenland looks like a frozen kingdom, a giant island buried under a sheet of ice so thick that in places it stands almost 2 miles deep. That ice has sat there for a very long time, locked up and solid, holding an unimaginable amount of frozen fresh water. Now it is melting, and fast. Every summer, the surface of the ice turns soft and wet. Rivers of meltwater carve across the ice and pour off the edges into the sea. Huge chunks break off the coast as icebergs and drift away to melt. Year after year, Greenland is shedding ice faster than fresh snow can replace it. The island is losing billions of tons of ice, and almost all of that fresh water ends up in the ocean. Here is the cruel part. It ends up in the North Atlantic. The same North Atlantic where the conveyor needs the water to stay salty and heavy so it can sink. Remember the weight belt. Salt and cold are what let the water plunge into the deep. Fresh water is the opposite of salt. Pour enough fresh meltwater onto the surface up there, and you dilute the sea. You make it lighter. You loosen the belt. Picture a swimming pool with a heavy drain at the bottom pulling water down. Now imagine someone floating a thick layer of light, fresh water on top. That fresh layer is too light to sink. It sits there like a lid, and it can smother the drain beneath it. The water that should be plunging into the deep gets trapped at the surface instead. That is the fear. Greenland's meltwater could act like a lid over the conveyor's engine right where it sinks. The more the planet warms, the more Greenland melts. The more Greenland melts, the more fresh water pours in. The more fresh water pours in, the harder it becomes for the ocean to sink and keep the conveyor running. Scientists are confident Greenland is melting, and confident the melt is speeding up. Satellites have watched it happen for years. The ice loss is measured, real, and not in serious doubt. What they are still working out is the tipping point. How much fresh water is too much? How close is the conveyor to the edge where the sinking fails and the whole system lurches into a weaker state? That number is one of the biggest questions in climate science today, and no one can pin it down with certainty yet. There is a haunting reason they take this so seriously. This exact recipe, a warming world dumping fresh meltwater into the North Atlantic, has played out before. And the last time, the conveyor did not just slow, it shut down and the climate flipped. We will get to that story soon because it is one of the strangest chapters in the history of our planet. First, though, there is a simpler question. How do we even know any of this is happening right now? The conveyor is hidden underwater more than a mile deep, spread across an entire ocean. You cannot walk up and read its speed off a dial. So scientists built something clever. They strung a line of machines all the way across the Atlantic, and they have been listening to the conveyor's heartbeat for about 20 years. To measure a current the size of an ocean, scientists had to string a tripwire across the entire Atlantic. Think about the problem. The conveyor is enormous, invisible, and buried deep. It stretches thousands of miles wide and more than a mile down. You cannot see it from space. You cannot feel it from a ship. Yet scientists needed to know exactly how much water it moves, and whether that amount is changing. So they built a line of sensors. Starting in the early 2000s, they dropped moorings across the Atlantic at a chosen latitude, a line running roughly from the coast of Florida over to the coast of Africa. Each mooring is a cable anchored to the seafloor, studded with instruments, reaching up through the deep. Together they act like a checkpoint, measuring the water flowing past. Picture a highway with no toll booths, and you want to know how many cars pass each day. So you build a row of counters straight across every lane. Nothing gets by without being measured. That is what this line of moorings does to the ocean. It counts the water, lane by lane, top to bottom. These instruments track the things that matter: how fast the water moves, how warm or cold it is, how salty it is. From all of that, scientists can add up the total flow of the conveyor and watch how it changes from week to week and year to year. For about 20 years now, this underwater checkpoint has been sending back a steady stream of numbers. It was a huge effort. The moorings sit in a punishing place, battered by storms and pressure and cold. Ships have to sail out and service them, haul them up, swap the instruments and drop them back down. It is slow, expensive, difficult work, done far from land in rough seas. Why go to all that trouble? Because before this line existed, scientists were mostly guessing about the conveyor's strength from year to year. Now they can actually watch it. For the first time in history, humans can see the pulse of the Great Current, close to real time. And the pulse is wild. Here is the surprise that came out of all this measuring. The conveyor does not flow at a smooth, steady rate. It swings up and down all the time. In the space of a few days, the amount of water it moves can jump dramatically, then drop just as fast. It is jumpy, restless, and full of noise. That jumpiness is a problem, and it sits at the heart of the argument. When a current swings around this much on its own, it becomes very hard to tell a real long-term slowdown from ordinary ups and downs. If you only have about 20 years of data, and the current jerks around wildly inside those 20 years, how sure can you be about the big trend? That single question has split the world of ocean science into two camps. One side looks at the data and sees a current in trouble. The other side looks at the same data and says it is too soon to be sure. Both sides are careful. Both sides are honest, and they strongly disagree. To understand why, we have to sit down at the table where these scientists argue and hear both of them out. Two groups of smart, careful scientists look at the very same ocean, and they see opposite things. Start with the worried camp. These researchers look at the warning signs and see a current already in decline. They point to the cold blob south of Greenland, the wrong colour in a warming world. They point to Greenland's melting ice pouring fresh water into the engine. They point to models that show a conveyor losing strength. To them, the pattern is clear and the direction is down. Now hear the cautious camp, because they are not careless people. Their argument is simple and strong. The direct measurements from that underwater checkpoint only stretch back about 20 years. And inside those 20 years, the current swings around so wildly that a real trend is hard to prove. One well-known study, looking at how the ocean gives up heat to the air, argued that the conveyor has held roughly steady since the middle of the last century. Their message is not that everything is fine forever. Their message is that the record is too short and the ocean too noisy to call a long-term slowdown just yet. So who is right? Right now, honestly, we do not fully know. This is a live scientific argument, not a settled fact, and anyone who tells you otherwise is selling something. The conveyor might already be slowing. It might be holding steady for now. The tools we have cannot yet close the case with total certainty. That uncertainty is uncomfortable, but it is important, and it cuts both ways. It means the scariest headlines might be early. It also means the calmest reassurances might be wrong. The truth is that we are watching a giant machine with a flashlight and a stopwatch, trying to judge its health from a short, jumpy peak. Here is the trap inside all of this. 20 years of clear data is not very long for an ocean that moves on a 1,000-year cycle. To really know what the conveyor is doing, you would want centuries of records. But nobody was dropping sensors into the deep Atlantic hundreds of years ago. The detailed measurements simply do not exist that far back. That gap could have ended the story. If we can only measure the conveyor for 20 years, and 20 years is too short to be sure, then maybe we are stuck. Except scientists refuse to be stuck. If the ocean did not keep written records, then it must have kept records of another kind. Nature is always writing things down if you know how to read them. The trick is finding the pages. So a different group of researchers went hunting for the conveyor's history in strange places. in the shells of tiny sea creatures, in layers of mud on the ocean floor, in patterns of temperature stretching back long before any instrument existed. They became detectives of the deep past, piecing together the strength of a current from clues it left behind without meaning to. And what they found, buried in those clues, was more alarming than the short record ever showed. If the ocean will not tell you its past directly, you have to read the diary it kept by accident. Here is the clever idea. Scientists could not measure the conveyor centuries ago, so they looked for things that recorded its behaviour on their own. Nature is full of these hidden diaries. You just have to know how to open them. One diary is temperature itself. A strong conveyor keeps that patch south of Greenland warm by hauling heat north. A weak conveyor lets it cool. So by piecing together sea temperatures across the whole Atlantic, going back well over a century, scientists could work out how the current must have been behaving to produce them. The cold blob, in other words, is a page in the diary. Another diary sits on the seafloor. Every year, dust, sand, and the remains of tiny creatures drift down and settle into mud. Layer builds on layer, like pages stacking in a book. The type of grain in each layer can hint at how fast the deep water was flowing when it was laid down. Fast deep currents drop heavier grains, slow currents drop finer ones. Read the layers in order, and you get a rough record of the conveyor's speed across thousands of years. There is a third diary, and it is beautiful. Tiny sea creatures build their shells out of the water around them. The chemistry of that water leaves a mark inside each shell. Gather enough of these shells from the mud, sort them by age, and you can reconstruct what the ocean was like when each one was alive. Millions of microscopic shells, each one a single line in a very long story. Scientists gathered all of these clues together from many places and many methods, and lined them up. And the picture that came out made people sit up. By their reading, the conveyor is now weaker than it has been in more than 1,000 years, slower than it was through centuries of history. According to this work, the current is not just wobbling inside its normal range. It has drifted to the low end of anything seen in a very long time. Honesty matters here too. These diaries are not as sharp as a modern instrument. Reading mud and shells and old temperatures takes careful guesswork, and different teams read the pages a little differently. This is strong evidence, and it is taken seriously, but it is a reconstruction, not a direct photograph. Still, put it all together and the trend leans one way. A short record that shows a jumpy, possibly slowing current, a cold patch in the wrong place, melting ice feeding the engine, and now a long history suggesting the conveyor is near its weakest in 1,000 years. None of these alone proves a crisis. Together, they make a lot of scientists nervous. There is one more thing that turns nervousness into real fear, and it has nothing to do with how fast the conveyor is slowing today. It is about how this kind of system behaves when it is pushed too far. A slowing current sounds like a gentle thing, a dimmer switch fading a light down bit by bit. You might expect it to ease off slowly, giving everyone time to adjust. The conveyor may not work that way at all. It may work like a switch that snaps. Some things fade away slowly, and some things break all at once, and the difference decides everything. Picture turning down a dimmer switch on a lamp. The light fades a little, then a little more, smooth and gentle. If you do not like it, you turn the knob back and the brightness returns. Nothing sudden, nothing lost. That is how many people imagine a slowing ocean current, a gentle dimming that we could always undo. Now picture a different switch. A normal light switch on the wall. You push it slowly, slowly, and for a while nothing happens at all. The room stays lit. Then you cross one tiny point and the light snaps off. No warning, no middle setting, on, then off, in an instant. Scientists fear the conveyor is the second kind of switch. The reason lies in how the current feeds itself. Remember the loop. Salty water flows north, cools, sinks, and pulls more salty water up behind it. The saltiness keeps the sinking going, and the sinking keeps the salty water coming. Each part props up the other. That kind of loop is strong right up until it is not. As long as it holds well, brushing off small changes, but push it past a certain point, and the loop can turn against itself. Weaker sinking lets fresher water build up. Fresher water weakens the sinking even more. The very cycle that kept the conveyor strong now drives it down, faster and faster, feeding on its own collapse. Think of leaning back in a chair, balancing on the two rear legs. You can tilt a long way and still catch yourself. The chair feels stable. Then you pass one invisible point, and there is no catching it. You are going over, and nothing you do in that last instant will stop it. The conveyor may have a tipping point exactly like that, a line you cannot see until you have already crossed it. This is the difference between a dimmer and a cliff. A dimmer you can always turn back up. A cliff, once you step off, does not care how sorry you are, and there is a cruel twist. Even after the conveyor tips and starts to collapse, the water might keep moving for a while, coasting on its old strength like a spun top slowing down. So the early stages could look almost calm. By the time the change is obvious, the system may already be past the point of return, tumbling toward its new, weaker state with no way back. Scientists have understood this idea in theory for a long time. Simple models showed decades ago that the conveyor could have two settings, a strong one and a weak one, with a sudden jump between them. The hard part was proving it could really happen in the messy, complicated real world, not just in a simple sketch. For years, the big, detailed climate models could not quite capture a full tipping event. The conveyor would weaken in them, but it would not snap. That left a gap. Was the tipping point real, or just a quirk of the simple math? Then, a few years ago, a team ran one of the most careful experiments ever attempted on this question. They pushed a full, complex model of the whole planet slowly and patiently toward the edge. And for the first time, they watched the conveyor go over the cliff. For the first time, scientists took a full model of the entire planet and pushed the ocean until it broke. Here is what they did. They took one of the big, detailed climate models, the kind that tries to capture the whole world, oceans, air, ice and all. Then they slowly added fresh water to the North Atlantic, a tiny bit more each year, mimicking the kind of melting and freshening the real ocean is facing, and they waited, and waited. This experiment ate up so much computer time that it ran for what felt like forever, inching the ocean toward its edge. For a long stretch, the conveyor held. It weakened slowly, the way the cautious scientists might expect. Then it reached a certain point, and everything changed. The current did not keep gently fading. It collapsed. In the space of about one model century, the mighty conveyor fell apart and dropped into a weak, broken state. The switch had snapped. This was a landmark. It was the first time such a complete, realistic model had ever shown the conveyor fully tipping over, start to finish. It proved the cliff is not just a trick of simple math. In a rich, detailed version of our planet, the tipping point was real. Then the scientists went further, and this is the part that made headlines. They studied the collapse to find a warning sign. They wanted something you could watch in the real ocean that would tell you the tip was coming before it arrived. They found one hidden in the flow of fresh water at the far southern edge of the Atlantic. In the model, that measure dipped to a low point years ahead of the collapse, like a needle sliding toward empty before the engine finally dies. Then they checked that same warning sign against the real world, using the best data we have of the actual ocean, and the finding was chilling. The real Atlantic appears to be moving in the same direction the model moved right before it tipped. In their words, the present-day conveyor looks like it is on a tipping course. That phrase spread around the world, and you can see why. It suggests the real ocean may be walking toward the same cliff the model fell off. Now, the honesty this deserves. This is one study using one model, and models are not the real world. They are careful guesses, powerful but imperfect. Other scientists raised fair questions. The model is coarse, and it cannot capture every twist of the real ocean. The warning sign is clever, but it is new, and it has not been fully tested by time. Some researchers think the danger is close. Others think this particular alarm rings too early. The debate is loud and ongoing. What almost no serious scientist does is wave the whole thing away. The study did something that cannot be unseen. It showed, in a realistic world, that the conveyor can collapse suddenly, and it offered a reason to think the real ocean is heading the same way, which leaves the single hardest question of all, the one everyone wants answered and no one can answer cleanly. If this is coming, when? Next decade? Next century? Never. The guesses are all over the map and the gap between them is enormous. Ask a room full of scientists when the conveyor might collapse, and you will get answers that span lifetimes. This is the question everyone wants pinned down. A date, a year, something to circle on a calendar. And it is the question the science is least able to answer with confidence. Look at the range. One well-known study, using a statistical method, suggested the conveyor could reach a tipping point surprisingly soon, sometime around the middle of this century, though with a wide window of uncertainty stretching decades on either side. That estimate landed like a thunderclap and made news around the world. Other studies pushed the danger much further out. Some of the big climate models suggest the conveyor might not fully collapse until after the year 2100, if it collapses at all, and even then mostly under the harshest warming. And a fair number of careful researchers argue that a full shutdown this century remains unlikely, even while they agree a weakening is real. So the honest range runs from within a few decades to beyond the next century, with a real chance it does not fully tip in our lifetimes at all. That is a huge spread. It is the difference between a problem for you and a problem for your great-grandchildren. Why can nobody narrow it down? Because every piece of this puzzle carries uncertainty. We do not know exactly how fast Greenland will melt. We do not know exactly how much fresh water the conveyor can take before it tips. We do not know exactly how the ocean and air will push on each other as the world warms. Stack all those unknowns together, and the timing blurs into a wide fog. There is something almost maddening about this. The stakes could hardly be higher, and the timing could hardly be blurrier. If we knew the conveyor would collapse in 10 years, the world would move heaven and earth to stop it. If we knew it was centuries away, we could plan calmly. Instead, we sit in the uncomfortable middle, with a serious risk and a fuzzy clock. One leading scientist put the challenge in a sharp way. The goal, he argued, is not to wait until we are certain the collapse is coming. By the time we are certain, it would already be too late to stop because a system this huge cannot be turned around quickly. The goal is to rule the disaster out, to be almost completely sure it will not happen, and right now, we cannot rule it out. That is a strange and heavy place to stand. We are not confident it will happen. We are also not able to promise it will not, and for a change this big, that uncertainty alone is reason to pay close attention. So if the future is this cloudy, where can we look for a clearer view? There is one place, the past. Because this has all happened before, not in a model, not in a guess, in reality, on this planet, to real living things, including our own ancestors. Long ago, the world was warming out of an ice age, much as it is warming now. Fresh water flooded the North Atlantic, and the conveyor did exactly what these studies fear. It shut down, and the climate turned on a dime. That ancient collapse has a name, and it began with a strange clue in the dirt. Almost 13,000 years ago, the world was warming up, and then, without warning, it slammed back into the cold. Set the scene. The Great Ice Age was ending. For thousands of years, huge sheets of ice had covered much of North America and Europe. Now the planet was warming, the ice was pulling back, and life was spreading north into the thawing land. Things were getting better. The long freeze seemed to be over. Then the world reversed. Temperatures across the north crashed back toward Ice Age cold and stayed there for more than 1,000 years. The thaw stopped. The ice held its ground. It was as if the planet had climbed halfway out of a frozen pit and then tumbled right back in. Scientists have a name for this backward lurch. They call it the Younger Dryas. It is a strange name, and the story behind it is oddly gentle for such a brutal event. There is a small white Arctic flower called the Dryas that thrives in cold tundra. When the deep cold returned, that flower spread into places that had started to warm. Much later, scientists digging through ancient dirt found the flower's traces exactly where warm forests should have been growing. That was the first clue. Pollen from a cold-loving flower buried in layers of earth in regions that should have been mild by then. The plants were telling a story the written history could not, because there was no written history. This was long before cities, before farming had truly taken hold, before anyone could record what was happening. The people alive then felt all of it. Our ancestors were hunters and gatherers, following animals across the land, living off what they could find. For them, the return of the deep cold was a catastrophe with no explanation. The animals moved. The plants died back. The world they had slowly learned turned hostile again, and they had to survive it with nothing but their wits and each other. Now, hold this next to today. Back then, the trigger was a warming world at the end of an ice age. Today we have a warming world again. Back then, the warming led to fresh water flooding the North Atlantic. Today, Greenland is sending fresh water into the very same sea. The setup rhymes, And that is exactly why scientists study this ancient event so closely. It is the closest thing we have to a real-world test of what a conveyor collapse does. And this is the crucial part. Scientists are confident the conveyor was involved. The clues in the mud, the shells, the ice, and the pollen all point the same way. When the deep cold returned, the great Atlantic current had weakened or stopped. The heat delivery to the north had failed, and the world above it froze. So the obvious question is, what turned the conveyor off in the first place? What flipped the switch and plunged the north back into the cold for 1,000 years? The answer is one of the most dramatic events in the history of our continent. It began far inland, in the middle of North America, with a lake unlike any that exists today. A lake held prisoner behind a wall of ice, and one day that wall gave way. In the middle of North America, a lake bigger than the Great Lakes sat trapped behind a wall of ice, waiting. As the Ice Age ended, the vast ice sheets covering the continent began to melt. All that meltwater had to pool somewhere. In the heart of the land, an enormous lake formed, fed by the dying glaciers. It grew and grew until it became one of the largest lakes the world has ever known. At its peak, it held more water than all 5 of the Great Lakes put together. A freshwater sea in the middle of the continent. What held this giant lake in place was the ice itself. A wall of glacier stood between the lake and the ocean, like a dam made of frozen mountains. For a long time, that icy dam held the water back. The lake stayed penned in, swelling with every year of melt. Then the dam failed. As the climate warmed, the ice wall weakened, and at some point it broke. The trapped lake burst free. A staggering flood of fresh water roared out across the land and poured into the North Atlantic. It was one of the greatest floods our planet has ever seen. A sudden release of a freshwater sea into the ocean. Now remember what freshwater does to the conveyor. The engine near Greenland runs on water that is cold and salty and heavy enough to sink. Freshwater is light. It floats. Dump an ocean's worth of fresh water onto the North Atlantic and you smother the sinking. You throw a lid over the drain. That is exactly what scientists believe happened. The flood spread a layer of light fresh water across the top of the North Atlantic. The heavy sinking that drives the conveyor stalled. The great current that carries heat north weakened or stopped. And with the heat delivery cut off, the North plunged into the long cold of the Younger Dryas. This is the leading explanation, and it is well supported. Scientists have mapped the ancient flood channels carved into the land. They have found signs in ocean sediments that the North Atlantic turned fresher at just the right moment. And when they force this kind of flood into their models, the models produce the same deep cold that really happened. The pieces fit. Honesty still matters. A few details remain debated. The exact path the flood took, and whether one flood alone can explain the whole event, are still argued over. Some scientists think other forces may have played a part in the timing. The big picture, fresh water shutting down the conveyor, is widely accepted. A few of the fine points are still open. Here is why this ancient story should make us pause. The recipe, then, was a warming world melting ice, sending fresh water into the North Atlantic, stalling the conveyor. The recipe now is a warming world melting Greenland, sending fresh water into the same North Atlantic, threatening the same conveyor. History does not have to repeat, but it is showing us, in stone and mud, exactly how this machine can fail. There is one more thing about the Younger Dryas that turns a scary story into a terrifying one. It is not how bad the cold got, though it was severe. It is how fast it arrived. The cold did not creep in over centuries. It crashed down in a single human lifetime, maybe faster. You might imagine a change this big taking ages. A slow slide into cold, generation by generation, so gradual that no one alive would notice it inside their own years. That would be bad enough. But the ice holds a record, and the record says something far more frightening. Deep in Greenland, the ice is stacked in yearly layers, like the rings of a tree. Each layer traps a little of the air and chemistry of the year it fell. Drill down and pull up a long core of that ice, and you can read the climate year by year, going back tens of thousands of years. It is one of the finest diaries our planet keeps. When scientists read the layers from the start of the Younger Dryas, they found the cold arrived shockingly fast. In parts of the north, temperatures fell by close to 20 degrees in a matter of decades. Some evidence hints it could have happened even quicker, within years, not centuries. A person could have watched their homeland turn from warming and green toward frozen and harsh inside their own lifetime. Sit with that speed for a second. A drop of close to 20 degrees is the gap between a livable climate and a punishing one, and it did not take 1,000 years to happen. It took less time than it takes a child to grow into an elder. The world flipped while people watched, then the cold dug in and stayed. The Younger Dryas held its grip for more than 1,000 years. That is over 1,000 years of harsher winters, shorter growing seasons, and a colder, drier world across the north. Our ancestors did not just survive a bad spell, they lived through 40 generations of it before the warmth finally returned. This is what makes the tipping point idea so serious. The conveyor did not ease off gently back then. It snapped, and the climate lurched with it, fast and hard. This is the real-world proof behind all those model warnings. A sudden collapse is not just possible in a computer. It has already happened here, on this planet, and it happened quickly. Now weigh the honest parts against the alarming ones. The world then was different from the world now. There was far more ice sitting around ready to flood the ocean than there is today. Some scientists argue that makes a Younger Dryas style crash less likely for us. That is a fair and important point, and it offers real reason for hope. Yet the core lesson stands. This system can flip fast. When the conveyor fails, the change does not wait politely for us to prepare. It can arrive inside a single lifetime, faster than farms and cities and coastlines can adjust. Speed is the danger as much as the cold itself, and the Younger Dryas was one event among many. The deep past shows this was not a lonely accident. The conveyor has stumbled and stalled again and again across the ages, each time reshaping the world above it. To see just how often this ocean has broken its own rhythm, we have to look back further still, deep into the frozen history of the planet, where the same story plays out over and over. The Younger Dryas was not a one-time accident. The conveyor has broken down over and over deep into the past. When scientists first pieced together the Younger Dryas, it looked like a single strange event. A freak flood, a freak freeze, a story that happened once and never again. Then they dug deeper into the ice and the mud, reading further back in time, and they found something that changed the whole picture. This had happened before, many times. Look across the last 60,000 years, and the record shows the conveyor faltered again and again. By careful counts from ice cores and seabed sediments, the Great Atlantic Current appears to have collapsed or nearly collapsed at least 7 separate times. 7. Each one reshaped the climate of the North. Each one came, held for a while, and eventually passed. There is a whole family of these lurches. Scientists have found a repeating pattern of sudden climate swings during the ice ages, where the North would flip between colder and slightly warmer states, in a rhythm that plays out across the deep past. These swings show up clearly in the Greenland ice layer after layer like a heartbeat that keeps skipping and catching. Sit with what that means. The conveyor is not a rock-solid machine that ran perfectly until humans came along. It is a system with a history of stumbling. Under the right push, it slows, it stalls, it recovers, and sometimes it crashes hard. This is simply something the Atlantic does when conditions line up the wrong way. Here is why that history matters so much for us. If the conveyor had only ever failed once, you could call it a fluke, a freak accident unlikely to repeat. But a system that has tipped 7 times over is a system with a known weakness. It is a door that has been kicked open before and can be kicked open again. Each collapse in the past needed a trigger, usually some surge of fresh water or heat that unbalanced the sinking near the north. Today, we are supplying our own trigger. A warming world, melting ice, fresh water pouring into the North Atlantic. We are pressing on the same weak spot that has given way so many times before. The honest side deserves a hearing. Those ancient collapses happened in a colder, icier world, with giant ice sheets ready to flood the sea. Our world is warmer and holds far less of that ready ice, so the exact same trigger is harder to pull now. Some scientists take real comfort from that difference, and it is a fair thing to hold on to. Yet the deeper lesson is hard to shake. This ocean has a track record. It has flipped many times, sometimes quickly, always with heavy effects on the world above. We are not looking at a machine that has never failed. We are looking at one that fails on a schedule we do not fully control. For most of this journey, the danger has felt far away, out at sea, buried in ancient ice, or hidden in models of the future. Now it is time to bring it home. Because if the conveyor slows, One of the very first places on Earth to feel it would be the coastline of the United States, and the way the sea would rise there is stranger than you might expect. Here is something that sounds impossible. When the current slows down, the sea along the American coast climbs up. You might think a weaker ocean current would have little to do with the tide outside a house in Boston or New York. The connection is real, and it comes from something you can picture with your own hands. Start with a surprising fact. The ocean is not perfectly flat. A strong, fast current can actually tilt the surface of the sea, piling water higher on one side than the other. The Gulf Stream does exactly this. As it races north along the American coast, the spin of the Earth pushes the flowing water sideways, away from the shore. That constant push tugs water off the coast and holds the sea surface a little lower against the eastern United States. So the strong current has been doing coastal cities a quiet favour for a very long time. By pulling water away from the shore, it keeps the local sea level lower than it would otherwise be. Most people have no idea the ocean off their beach sits lower because of a current they have never seen. Now, weaken that current. As the Gulf Stream slows, its sideways push fades. It stops tugging the water away from the coast, and all that water it was holding offshore comes sliding back toward land. The sea leans in, the level rises along the eastern seaboard. Picture spinning a bucket of water in a circle. While it spins fast, the water climbs the outer wall and dips in the middle. Slow the spin, and the water sloshes back and settles flat. The coast of the United States sits where the water would come sloshing back. This is why scientists warn that a weakening conveyor would hit the American coast especially hard. The rise from a slowing current comes on top of the sea level rise the whole world is already facing from melting ice and warming water. It stacks. The global rise lifts every coast. This extra tilt effect piles more water onto this one coast in particular. How much more? Studies suggest a serious slowdown could add something like an extra 0.5 metre or more to the sea along the east coast, on top of everything else, over the coming century. That is well over a foot of extra water, aimed straight at the streets, subways and airports of the most crowded shoreline in the country. Scientists are fairly confident about the direction of this effect. The physics linking a slower current to a higher coastal sea is well understood, and there are already hints of it in the records off the northeastern United States, where the sea has been climbing faster than the global average. The exact size and speed are still being pinned down, but the basic warning is solid. This is the moment the whole story stops being about a distant ocean and starts being about a doorstep. A current far out at sea, slowing over decades, could push the tide up against real cities where real people live, and when the water climbs by that much, the danger is not some rare, once-in-a-lifetime flood. It is the ordinary high tide on an ordinary day, arriving in places it never used to reach. Raise the sea by a foot or two, and the rare disaster becomes the everyday nuisance. People tend to think of coastal flooding as a big dramatic event. A hurricane roars in, the water surges, the news shows flooded streets, and then it recedes and life goes back to normal. That is the flood we picture, sudden, severe, and gone in a day. A slowly rising sea works differently, and in some ways it is worse. It does not need a storm, it simply raises the baseline. The normal level the water starts from every single day. And when the baseline creeps up, the floods that used to be rare start happening all the time. Think about it like filling a bathtub closer to the rim. When the tub is half full, a splash does nothing. Fill it near the top, and the same small splash sends water over the edge and onto the floor. Raise the sea against a city, and the same ordinary high tide, the same ordinary storm, now spills over walls and into streets that used to stay dry. This already has a name along the American coast: sunny day flooding, water bubbling up through storm drains and pooling in the streets on a clear, calm day, with no storm in sight, just because the high tide has climbed high enough to reach. It is happening more often already. Push the sea higher, and it happens far more. Now picture the cities in the path, the low-lying streets of Miami, where the ocean already seeps up through the ground on high tides, the packed shoreline of New York with subways and tunnels running below the waterline, the historic waterfront of Boston, countless smaller towns strung along the coast, built for a sea that sat lower than the one they would face. A flood that used to strike once in a great while could start arriving many times a year. Roads that flooded rarely could flood on a regular basis. The machinery of a city, its trains, its power, its basements, its roads, all of it was built for the old sea level. Raise the water, and you are fighting the ocean every month instead of every decade. The cost of that is enormous, and much of it is quiet. It is not only the dramatic rescues, it is the slow drip of damage. Saltwater rotting the underground pipes and cables, higher insurance that prices families out of their homes, neighbourhoods that flood so often people finally give up and leave, a shoreline that retreats one soggy street at a time. Scientists are confident about the basic math here. More sea plus the same storms equals more flooding, more often. That part is simple and sure. The hard part is the timing, because it depends on how fast the conveyor weakens and how fast the world's ice melts, and both of those still carry real uncertainty. This is the heart of the serious question for America. A change in a hidden ocean current could reshape the daily life of the nation's coasts, turning rare floods into routine ones across the most crowded shoreline in the country. But America is only one side of this ocean. Cross to the far shore, and the same weakening current does something almost opposite and just as unsettling. Because while the American coast drowns, Europe would begin to freeze. The same slowing current that floods America would leave Europe out in the cold. We already know why Europe is mild. The conveyor hauls warm water north and hands its heat to the winds that blow across the continent. That borrowed warmth is the only reason places like Britain, France and Scandinavia stay green through winter instead of frozen like the far north of Canada at the same latitude. Now take that warmth away, slow the conveyor, and less heat arrives up north. The delivery that keeps Europe mild starts to fail, and the farther north and west you go, the colder it would bite. Britain and the countries near it sit right where the warm water gives up the most of its heat, so they would feel the loss the hardest. How cold could it get? A full collapse of the conveyor could drag winter temperatures across parts of northern Europe down by many degrees. Some studies of a hard shutdown show brutal winter cooling over Britain and Scandinavia, enough to bring the kind of deep, biting freeze those countries almost never see today. Picture London facing winters more like a harsh Canadian city. Picture ports and roads and farms built for mild weather suddenly slammed by ice. The strange thing is that this would happen even as the planet as a whole keeps warming. Most of the world would still be heating up from greenhouse gases, but this one region, robbed of its ocean heat, could buck the global trend and turn colder. A pocket of deep freeze inside a warming world. There is more than cold to worry about. A shift in the ocean could also change where the winter storms travel. The Atlantic already hurls storms at Europe every winter. A weakened conveyor and a colder North Atlantic could shove those storm tracks around and, some studies suggest, make certain storms fiercer. Harder winds, heavier rain and snow, a rougher, wilder cold season slamming the western edge of the continent. Think about how much of Europe is built around a gentle climate. Farms depend on mild winters and long-growing seasons. Cities are built without the heavy defences that truly frozen places need. Energy systems are sized for moderate cold, not for deep, sustained freezes. A sharp turn toward colder, stormier winters would strain all of it at once. Honesty is important here too. The worst versions of this come from studies of a full conveyor collapse, which is the extreme case, not the guaranteed one. A partial slowdown would be milder than a total shutdown, and how hard Europe would actually cool depends on the tug-of-war between the warming world and the fading current. Scientists are still working out where that balance would land. Even so, the basic picture is agreed upon. The conveyor is a huge part of why Europe is livable the way it is. Weaken it, and the continent that leans on that ocean heat would feel the ground shift under its feet. So we have a strange split across one ocean. America's coast climbing under rising water, Europe's winters plunging toward the cold, one current, two opposite blows, yet even that split hides a twist, because the cooling in Europe might not be the simple, year-round chill you would expect. In the middle of colder winters, the very same broken current could deliver something that sounds impossible. Hotter, drier summers. Here is a riddle. How can a colder ocean give Europe hotter summers? The answer surprised even the scientists. Everything we have said points one way. The conveyor keeps Europe warm, weaken it, and Europe cools. That is the simple story, and for winter it holds up well. Colder winters make sense when the ocean heat delivery fails. Summer, it turns out, may be stranger. Scientists went back to the last great collapse, the Younger Dryas, to study it in fine detail. They expected to find that European summers back then had turned cold too, matching the frozen winters. So they gathered clues from ancient plants, the kinds of species that only grow within certain temperatures, to reconstruct what those long-ago summers were actually like. The plants told an unexpected story. While the winters were savage, the summers had stayed surprisingly warm, in some places hot and dry. The cold did not spread evenly across the whole year. It hammered the winters and spring, then eased its grip in summer, leaving the warm season strangely intense. Why would that happen? The answer lies in the winds. A colder North Atlantic can change the way air moves over Europe. It can encourage a pattern where the weather gets stuck, where a dome of still, dry air parks over the land and refuses to budge for weeks. Stuck weather in summer means the sun beats down day after day with no relief. The ground bakes, the rivers drop. A heat wave settles in and stays, so the same broken conveyor could hand Europe a brutal double life. Bitter, frozen winters on one end of the year, baking, dry heat waves on the other, a climate that swings hard in both directions, punishing in the cold season and punishing again in the warm one. For farms, this would be a nightmare. Crops are delicate. They need the cold to come at the right time and the heat to stay within limits. A world of vicious winters and scorching dry summers would batter agriculture from both sides. Growing seasons would shorten. Harvest would suffer. Water would run short in the very month plants and people need it most. The scientists studying this were careful about what it means for today. Their work suggests that even a partial slowdown of the conveyor, the kind that may be underway now, could tilt Europe toward more of these stuck weather heat waves and droughts in summer. In other words, some of the fierce heat and dryness Europe has already been facing might be linked, in part, to changes in this ocean current. The honest caveats stand. This is careful reconstruction of an ancient world combined with modelling, and models can miss things. Different studies weigh the summer effect differently. The exact size of the risk for modern Europe is still being worked out, and reasonable scientists disagree on the details. The larger point cuts through the debate. A weakening conveyor does not simply make one region a little cooler. It scrambles the whole rhythm of the seasons in ways that can seem to contradict themselves, cold and hot, all from the same cause. And the reach of this broken current stretches far beyond Europe and America. Follow its effects south, toward the middle of the planet, and you find something that touches the food supply of billions of people at once. A great belt of rain, and the threat that it could shift. There is a band of rain that circles the middle of the earth, and billions of people live and die by where it falls. Near the equator, where the warm halves of the planet meet, the air rises and dumps huge amounts of rain. This creates a great belt of wet weather that wraps around the middle of the world. It is one of the most important features of our climate, because it decides where the rains come each year. Whole civilizations are built around this rain belt. In places like West Africa and South Asia, the seasonal rains it brings are called the monsoon. Farmers wait all year for those rains. Their crops depend on them. When the monsoon arrives on time and strong, there is food. When it fails, there is hunger. For hundreds of millions of people, the timing of that rain is the difference between a full plate and an empty one. Now here is the link back to our ocean. That rain belt does not sit perfectly still. It can drift north or south depending on the balance of heat between the top and bottom of the planet. And the conveyor is a major part of that balance, because it carries so much heat from the southern half of the world up into the north. Weaken the conveyor, and less heat gets pulled north. The northern side of the Atlantic cools. That change in the heat balance can tug the whole rain belt southward, shifting it away from where it has sat for as long as anyone can remember. Move the rain belt, and you move the rains that feed billions. Picture a sprinkler set to water a garden. The plants have grown for years right where the water lands. Now nudge the sprinkler so it sprays a few feet to the side. Suddenly the old garden goes dry and the water falls where nothing was planted. Shift the rain belt and you do that to entire nations at once. The countries that could lose their rains are among the most crowded and most vulnerable on Earth. Across a wide stretch of Africa, a southward shift of the rain belt could bring long, punishing droughts. In parts of South Asia, the monsoon that waters the crops of hundreds of millions could weaken or arrive wrong. These are places where farming feeds enormous populations directly, where a failed rainy season is a true emergency. Scientists studying conveyor collapse consistently find this rain belt shift in their models. It is one of the most robust and widely agreed on effects. When the conveyor weakens in a simulation, the tropical rains move and the monsoons suffer. Different models argue about the exact size and pattern, but the direction shows up again and again. This is the moment the story grows truly global. A current in the Atlantic, slowing over decades, could reach across the world to dry out farmland thousands of miles away, on continents far from the ocean itself. This suffering would not stay near the sea. It would spread inland to fields and villages that have never given the Atlantic a second thought. And the reach does not stop there. Cross the ocean to South America, to the greatest forest on the planet, and the same shifting rains could turn its whole world upside down. The Amazon itself could be flipped inside out. The greatest rainforest on Earth runs on a careful schedule of wet and dry, and a broken ocean current could flip it backward. The Amazon is a living giant. It stretches across a huge part of South America, holds a staggering share of the planet's plant and animal life, and breathes out a large slice of the world's fresh air. All of that depends on rain, delivered in a rhythm the forest has followed for ages. A wet season when the rains pour down, a drier season when they ease off. The whole forest is tuned to that beat. Now bring back the shifting rain belt. We just saw that a weakening conveyor can drag the tropical rains southward and scramble where they fall. The Amazon sits right in the reach of those rains. Change the pattern, and you change the heartbeat of the forest. One study looked at what a full conveyor collapse might do to the Amazon, and the result was startling. It found the rainfall pattern could drastically change. In some areas, the dry season and the wet season could essentially swap places. The months that were supposed to be dry would turn wet, and the months that were supposed to be wet would turn dry. The forest calendar flipped. Think about how much depends on timing in nature. Trees flower and fruit on cue. Animals breed and migrate on cue. Rivers rise and fall on cue. The whole web of forest life is stitched together around knowing when the rain comes. Reverse that schedule and you tear the stitching. Plants bloom when there is no water to support them. Dry-loving creatures drown while wet-loving ones wither. The intricate machine of the rainforest jams. A forest thrown into that kind of chaos would be in serious danger. Stressed trees are weaker trees. Weaker trees are more likely to die, to burn, to fall, and the Amazon does something crucial for all of us. It pulls a vast amount of carbon out of the air and locks it away in wood and soil. A damaged, dying Amazon would not just be a tragedy for South America. It would release stored carbon back into the sky, feeding the very warming that started the whole chain of trouble. That is one of the cruelest parts of this entire story. Many of these effects can feed each other. A warming world weakens the conveyor. A weakened conveyor harms the Amazon. A harmed Amazon releases carbon that warms the world further. The pieces are linked, and pushing on one can push on all the others. The honest limits apply again. This Amazon flip comes from studying an extreme case, a full conveyor collapse, which is the worst scenario rather than the guaranteed one. Models of the rainforest are complicated and imperfect, and scientists debate how the forest would truly respond. This is a serious warning drawn from careful science, held with appropriate caution. Step back and look at the map of harm. Rising seas on the American coast, freezing winters and scorching summers in Europe, failing monsoons across Africa and Asia, a rainforest turned inside out in South America, all of it flowing from changes in one hidden ocean current, and we have only touched the effects on land. The ocean itself, the living sea, would feel this too. Because the conveyor does more than move heat. It carries the food that keeps the ocean alive. Slow it down, and the sea could start to go hungry. The conveyor does more than move heat around the planet. It feeds the ocean, and a hungry ocean is an empty one. We have followed this current as a mover of warmth. Now meet its other job. As the conveyor churns and sinks and rises across the world, it stirs the sea. It carries food, in the form of tiny nutrients, up from the deep and spreads it around the ocean. Those nutrients are the base of nearly all life in the sea. Here is how it works. Down in the deep, dead plants and creatures slowly sink and break apart, releasing a rich supply of nutrients into the cold, dark water. But life needs sunlight, and sunlight only reaches the top of the sea. So those nutrients are useless while they sit trapped in the deep. Something has to lift them back up toward the light. The conveyor and its currents are a big part of what does that lifting. When deep, nutrient-rich water rises toward the sunlit surface, It feeds an explosion of life. Tiny drifting plants bloom in the light, using those nutrients to grow. Those tiny plants are the grass of the sea. Small creatures eat them. Fish eat those creatures. Bigger fish eat the smaller fish. Seabirds and seals and whales feed on all of it. The entire ocean food web grows up from that base, and the base grows up from nutrients lifted out of the deep. Now slow the conveyor, weaken the stirring, less deep water rises, fewer nutrients reach the sunlit surface. The tiny plants at the bottom of the food web grow less, and when the base of the web shrinks, everything above it shrinks too. Fewer small creatures, fewer fish, emptier seas. Picture a farm where the tractor that spreads the fertilizer breaks down. At first the fields look fine. Then, without fresh nutrients, the crops thin out, and the animals that fed on those crops go hungry, and the whole farm slowly empties. A slowing conveyor could do that to a huge stretch of the Atlantic. The North Atlantic is one of the great fishing grounds of the world. For centuries, fleets have pulled cod and other fish from these waters to feed millions of people. Coastal towns on both sides of the ocean were built on that catch. A conveyor that fails to feed the sea could thin those fish stocks, hurting the fishermen, the towns, and everyone who eats from the Atlantic. There is a second blow underneath this one. Moving water also carries oxygen down into the deep. A sluggish conveyor could leave parts of the deep ocean starved of oxygen, making them hostile to the creatures that live there. A hungry ocean and a breathless one at the same time. Scientists are confident about the basic connection between ocean stirring and ocean life. That link is well established. The uncertainty is in the details, how much the food web would shrink, how fast, and exactly which fisheries would suffer most. Those specifics are still being studied. So add the sea to the list. The conveyor's slowdown reaches not only our coasts and our farms, but into the water itself, into the fish on the plate, and the life in the deep. There is one more corner of this ocean story that touches America directly, and it arrives every summer, spinning out of the warm tropics with a name people already fear. Every summer, America watches the tropical Atlantic with dread, because that warm water is where hurricanes are born. A hurricane is a heat engine. It feeds on warm ocean water. When the sea surface in the tropical Atlantic heats up, it pumps warmth and moisture into the air above, and that rising warm, wet air is the fuel a storm needs to grow. The warmer the water, the more fuel available, and the stronger a storm can potentially become. So the temperature of the Atlantic is tied directly to the storms that slam the American coast each year, and the conveyor helps set that temperature by moving heat around the ocean. Change the conveyor, and you change the pattern of warm and cold water that hurricanes rise from. This is where it gets tangled and honesty has to lead. The link between a slowing conveyor and future hurricanes is genuinely complicated, and scientists are careful about it. A weakening conveyor cools some parts of the North Atlantic, like the cold blob, while other parts, especially the tropics, may hold or build heat. Storms respond to that shifting map of warm and cold in ways that are hard to predict cleanly. Here is one worry that comes up. If the conveyor carries less heat away from the tropics, heat could pool in the tropical Atlantic, the exact nursery where hurricanes form. More heat in that nursery could mean more fuel for storms in the very region where they threaten the United States and the Caribbean most. That is a concern researchers take seriously. At the same time, the cold blob and other changes could shift the winds high above the ocean, and winds up there can either help storms grow or tear them apart. So the same broken conveyor might feed storms in one way while fighting them in another. The net result is not simple, and scientists openly say so. What many researchers do expect, more broadly, is that a warming ocean tends to make the stronger storms wetter and more intense, even if the total number of storms does not clearly rise. A hotter sea holds more moisture, and more moisture means heavier rainfall when a storm makes landfall. Combine that with the higher sea levels we already talked about, and the danger sharpens. A storm surge riding on top of a raised sea reaches farther inland than it ever could before. That is the real gut punch for the American coast. It is not only about how strong the storms get, it is about the water level they arrive on. Raise the baseline sea with a slowing conveyor, then send a storm surge on top of it, and floods that once stayed near the beach can push deep into cities. So the picture for hurricanes is a mix of the uncertain and the alarming. The exact effect of the conveyor on future storms is still debated, and reasonable scientists land in different places. But the surrounding facts, a warmer nursery for storms, wetter rainfall and higher seas beneath the surge, all lean toward a coast in greater danger. We have now traced the near-term threat to its edges: rising seas, frozen winters, failing rains, hungry oceans, fiercer floods, all from a current that might be slowing right now, which leaves one last haunting problem about this whole crisis. Even if it is coming, we may not be able to see it clearly until the moment we can no longer stop it. Here is the cruelest twist in the entire story. By the time we are certain the conveyor is failing, it may already be too late to save it. Think back to how this system behaves. It is enormous, slow, and heavy. It moves on cycles that take centuries, and it may work like a switch that snaps rather than a dial that eases. Those traits, which make the conveyor so powerful, also make it terribly hard to manage. Start with the size. Turning a system this big is like steering a giant ship. A supertanker cannot stop or turn on a dime. The captain has to act miles ahead of the danger, because by the time trouble is right in front of the bow, the ship's own weight carries it forward no matter what the crew does. The conveyor has that same crushing inertia. Push it toward the edge, and it keeps drifting that way long after you stop pushing. Now, add the snapping switch. If the conveyor has a tipping point, then before the tip it might look almost steady. It could weaken quietly, hovering near the edge, showing only small signs. Then it crosses the invisible line and collapses, and by then there is no easy way back. The calm before the fall is exactly what makes it so dangerous. It hides the emergency until the emergency is over. Put those together and you get an awful trap. To be completely sure the collapse is coming, we would want to watch it clearly begin. But if we wait for that clear proof, the system may already be past its tipping point, coasting toward collapse with too much momentum to reverse. Certainty and safety may not arrive at the same time. By the time we are certain, safety could be gone. One leading scientist framed the problem in a sharp and sobering way. He argued that the goal should not be to wait until we are sure the disaster will happen. The goal should be to rule it out, to become almost completely confident it will not happen. Because for a threat this size and this hard to reverse, being unsure is itself a reason to act. Right now we cannot rule it out. We cannot promise the conveyor is safe. That is a strange and heavy place for a society to stand. We are used to waiting for proof before we act. Wait for the fire before calling the fire truck. But a conveyor collapse is a fire you cannot put out once it starts. The only real defense is to keep it from starting at all, which means acting under uncertainty before the proof arrives. The honest truth runs both ways, as it has all along. The collapse might be decades off, or a century off, or it might not fully happen in our lifetimes. The uncertainty that makes it hard to rule out also means it may not strike soon. Nobody can hand you a date. What they can tell you is that this is a real risk, hard to see coming and hard to undo, which is exactly the kind of risk worth taking seriously early. So that is the near-future question hanging over America and the world. A hidden current, possibly slowing, with the power to reshape coasts and climates, and a warning that may come too late. Yet this is only the faster of two great changes moving through the Atlantic. Step back far enough, and a second, slower phase comes into view. One that does not threaten the current at all, but the entire ocean. Because oceans, it turns out, do not last forever. Here is something almost no one thinks about. Oceans are born, they grow, and one day they die. We treat the ocean as a permanent feature of the world. The continents in their places, the seas between them, fixed and eternal. That is how they look across a human life, or even across all of recorded history. But the Earth keeps a much longer calendar than we do, and on that calendar, oceans come and go. The ground beneath our feet is not solid and still. The outer shell of the planet is broken into giant pieces, like a cracked eggshell, and those pieces slowly move. They drift across the surface of the Earth at about the speed your fingernails grow. Too slow to feel, too slow to see, but relentless across millions of years. As those pieces move, they pull continents apart and shove them back together, and the oceans form and vanish in the gaps between. Scientists have a name for the full life cycle of an ocean. It runs like this. First, a continent cracks and splits. As the two halves pull apart, a new sea floods into the gap between them. That young sea widens over millions of years, growing into a full ocean. Then, at some point, the growth stops. The ocean begins to close as the continents drift back toward each other. Finally, the ocean is squeezed shut entirely, and the continents collide, throwing up mountains where the water used to be. Then someday, the cycle can begin again. This grand cycle takes hundreds of millions of years to complete. A single ocean can spend that long being born, growing, and dying. No creature ever witnesses the whole thing. It plays out across spans of time so vast that all of human history is barely a flicker within it. We already have proof this happens sitting right on the map. Look at the Mediterranean Sea, the water between southern Europe and northern Africa. That sea is what remains of a once mighty ocean that has been squeezed nearly shut as Africa pushes north into Europe. The Mediterranean is an ocean in its old age, most of it already gone, slowly being crushed out of existence. It shows us the closing phase in action. So oceans truly do die. This is settled science, built from decades of study of how the planet's surface moves. The rocks record it. Ancient seas that no longer exist have left their mark in the mountains and the crust. The Earth has opened and closed oceans many times over its long life. Which brings us to the Atlantic and to a question that sounds impossible at first. If every ocean has a life cycle, and every ocean eventually dies, then where in that cycle is the Atlantic right now? Is it young and still growing, or has it started the long turn toward its end? To answer that, we have to go back to the Atlantic's birth, to a time when it did not exist at all, when the lands on either side of it were locked together as one. The Atlantic has a birthday, and it is younger than you might think. The Atlantic Ocean has a birthday, and on the calendar of the Earth, it is still fairly young. Rewind the planet far enough, and the Atlantic is gone. In its place, the lands we now call the Americas sit pressed directly against Europe and Africa. All the major land masses are fused together into one enormous supercontinent, a single, sprawling mass of land surrounded by one vast ocean. Scientists call that ancient supercontinent Pangaea. If you could stand on that world, you could walk from what is now the eastern United States straight onto what is now northwest Africa, with no ocean in between. The bulge of Brazil fits snugly against the curve of Africa's coast, like two pieces of a puzzle. In fact, that puzzle fit is one of the clues that first led scientists to realize the continents had once been joined and had since drifted apart. Then, around 180 million years ago, Pangaea began to tear. A great crack opened through the supercontinent, and the two sides started pulling away from each other. Molten rock welled up into the widening gap and hardened into new seafloor. Water flooded in. A narrow new sea was born between the separating lands. That young sea was the infant Atlantic. From that moment on, the Atlantic has been growing. The two sides have kept drifting apart. A new seafloor has kept forming in the middle to fill the ever-widening gap. Down the centre of the ocean runs the seam where this happens, a vast underwater mountain range that stretches almost the entire length of the Atlantic. It is one of the longest mountain chains on the planet, and almost all of it is hidden beneath the waves. That underwater ridge is where New Atlantic is still being created today, and the ocean is still spreading right now, this very year. The Americas and Europe are drifting apart at roughly the speed your fingernails grow, a few centimetres every year. It sounds tiny, and it is. But multiply that by millions of years, and it adds up to an entire ocean. Every year the Atlantic gets a little wider. Every year America and Europe sit a little farther apart than the year before. So on the great life cycle of oceans, the Atlantic has spent its whole existence in the growing phase. Born from a crack in Pangaea, widening ever since, still spreading today. By that measure, it is a healthy, growing ocean in what you might call its prime. All of this is well established. The birth of the Atlantic from Pangaea, the underwater ridge that builds new seafloor, the slow spread of the continents, all of it is measured and mapped and agreed upon. We can even track the drift directly with modern instruments, which sets up the real puzzle. If the Atlantic is still growing, still widening year after year, then it should be a long, long way from dying. A growing ocean is a young ocean. And yet a group of scientists recently found the first hint that the Atlantic's growing days may be closer to an end than anyone assumed. They think the ocean may be quietly approaching the great turn, the moment when growing gives way to closing. The trouble is, to close an ocean you need something very hard to make, and for a long time it looked like the Atlantic simply did not have it. To make an ocean start closing, you need a very special kind of crack in the earth, and these cracks are almost impossible to build. Here is the puzzle that stumped scientists. An ocean grows when new seafloor is made in the middle and the continents drift apart. Simple enough. But for an ocean to close, the seafloor has to go somewhere. It has to be destroyed as fast as it is being made, or faster, and destroying seafloor takes a special feature, a place where the heavy ocean floor bends down and dives back into the depths of the earth. Scientists call these diving zones subduction zones. Picture two giant plates of the Earth's surface meeting, and one of them tipping down and sliding beneath the other, plunging into the hot interior of the planet. That is a subduction zone. It is like a slow-motion drain in the Earth's shell, swallowing old seafloor and pulling it down into the deep. Where these zones exist, oceans shrink. The seafloor gets consumed faster than it forms, and the ocean slowly closes. The Pacific Ocean is ringed with these diving zones. Around the edges of the Pacific, the seafloor is being swallowed on many sides at once. That is why the Pacific is dotted with volcanoes and rocked by earthquakes, forming the famous belt people call the Ring of Fire. The Pacific, in a sense, is being eaten alive around its rim. It is an ocean already in its closing phase. The Atlantic is different. Along most of its edges, the ocean floor connects smoothly to the continents, with no diving zones swallowing it. The Atlantic makes new seafloor in the middle but has almost nowhere to destroy it. So it just keeps growing. No drain, no closing. That is why it has widened for 180 million years without stopping. So for the Atlantic to ever close, brand new diving zones would have to appear along its edges. And here is the maddening catch. These zones are extremely hard to create from scratch. The Earth's plates are thick, strong, and stubborn. To start a new diving zone, you have to crack a plate and bend it downward, and plates do not want to break or bend. They resist. It is like trying to snap a fresh springy branch that just bows and refuses to break. For a long time, this looked like a paradox. Every ocean is supposed to close eventually, but closing needs diving zones, and diving zones almost never form on their own in a quiet ocean like the Atlantic. So how does a growing ocean ever begin to die? Scientists found a possible escape from the paradox, and it is clever. What if a diving zone does not have to be built from nothing? What if an existing one, already active in a nearby dying sea, could slowly migrate, creeping sideways over millions of years until it reaches into a fresh ocean? An old drain, wandering into new water. They gave this sideways creep a name: subduction invasion. One ocean's diving zone slowly invading another ocean, bringing the power to close it along for the ride. It was a neat idea. What it needed was a real example, caught in the act. A place on Earth where a diving zone from a dying sea is right now inching toward the open Atlantic, and a team of scientists believes they have found exactly that. It sits at a narrow gateway between two continents, a place whose name you already know. At the mouth of the Mediterranean, hidden beneath a famous strip of water, something is slowly creeping toward the Atlantic. Look at the map where Europe and Africa nearly touch. Spain reaches down toward Morocco, and between them runs a narrow channel, connecting the Mediterranean Sea to the open Atlantic. That channel is the Strait of Gibraltar. Ships pass through it every day. Most people know it as a landmark, a choke point, a line on a map. Beneath it lies something far stranger. Down under that region sits a diving zone, a place where the Earth's shell bends down and plunges into the deep. It belongs to the Mediterranean, the dying sea we met earlier, the shrinking remains of an ancient ocean being squeezed shut. This diving zone has been at work for a long time, helping consume the old Mediterranean seafloor as Africa pushes north. For millions of years, that diving zone crept westward, migrating slowly toward the Atlantic. Then, over the last few million years, it seemed to stall. Its motion slowed way down, so much that some scientists began to wonder whether it had died out completely, whether it was still active at all. It went quiet, and quiet can mean dead. A team of researchers decided to test that question with powerful computer models. They rebuilt the history of this region inside the simulation, tracking how the diving zone formed and moved over millions of years, and then let the model run forward to see what it would do next. Their goal was to find out whether the Gibraltar diving zone was finished, or merely resting. Their answer, published a couple of years ago in a respected Earth science journal, was that the zone is not dead. It is only in a lull, a quiet pause in a much longer story. According to their model, that pause will last a while longer, roughly 20 million years. and then the diving zone will wake back up, resume its westward creep, and push out past Gibraltar into the open Atlantic Ocean. That is the subduction invasion, caught in its earliest moment. An old diving zone from the dying Mediterranean, poised to invade the growing Atlantic. The lead scientist pointed out how rare and valuable this is. Studying Gibraltar lets researchers watch the very beginning of the process, the instant an ocean's fate starts to turn, something almost never visible in the geological record. This is worth marking honestly. This is a prediction from a computer model, not a certainty carved in stone. It reaches tens of millions of years into the future, and the deep future is genuinely hard to model. Other scientists may read the region differently. This is a fascinating and serious piece of science, held as a leading idea rather than a settled fact. But if the model is right, it means the Atlantic already has the seed of its own closing planted at its eastern gateway, a drain waiting to switch back on, and Gibraltar may not be alone. There are already a couple of small diving zones on the far side of the Atlantic, near the Caribbean and down toward Antarctica, other places where the ocean floor has begun, in small ways, to be swallowed. Add them all together, let them grow over the ages, and you get a vision of the Atlantic's distant future that turns the whole ocean into something it has never been. A ring of fire of its own. Give it 20 million years, and the Atlantic could begin to circle itself with fire and start to swallow itself whole. Here is the vision the scientists paint. Today the Atlantic grows, quiet and stable, widening year by year with almost nothing to consume its seafloor. But look ahead across the deep future, and that quiet ends. The sleeping diving zone at Gibraltar wakes and pushes into the ocean. The small diving zones already lurking near the Caribbean and toward Antarctica keep working and spreading. More may form as the old ones weaken the ocean's edges. Over millions of years, these diving zones could grow and link, wrapping around the edges of the Atlantic. The ocean floor, once safe, would start to bend down and plunge into the depths along its rims, and wherever seafloor dives into the earth, you get the signature that follows, chains of volcanoes and belts of earthquakes rising along the edges. That is exactly what rings the Pacific today. The Pacific's ring of fire is the band of volcanoes and quakes that circles it, marking where its seafloor is swallowed. The scientists behind this work suggest the Atlantic could slowly grow a ring of fire of its very own, an Atlantic version of that fiery belt forming over the next 20 million years and beyond. And once an ocean is ringed by diving zones swallowing its floor, its fate turns. The Atlantic would stop growing. It would tip over into the closing phase of the Great Cycle. The seafloor would be consumed faster than the middle ridge could build it, and slowly, across enormous spans of time, the ocean would begin to shrink. The Americas would stop drifting away from Europe and Africa and start ever so slowly drifting back. Sit with the scale of that. The Atlantic we know, this vast, growing, seemingly eternal ocean, would be caught in a slow-motion collapse inward. The very same water that Pangaea's breakup opened up would eventually be squeezed away again. In the far, far future, the continents on either side could close in and one day collide, crushing the Atlantic shut and raising new mountains where the open sea once rolled. This is the Wilson cycle completing itself. An ocean born from a cracking supercontinent, grown to full size, then closed again as the lands reunite. The Atlantic would be living out the same life story that the ancient Mediterranean's parent ocean already finished. Birth, growth, and death, written across the face of the planet. The honesty here is important, because the timescales are almost unreal. This is tens of millions of years away at the earliest. No human, no city, no country will be around to see it in any form we would recognize. It is a forecast for a world so distant that our entire species might be unrecognizable, or gone long before the first Atlantic volcano rises, and it rests on models of the deep future, which are powerful but uncertain. This is a leading scientific idea about where the Atlantic is headed, not a guaranteed schedule. Still, the meaning is staggering. The Atlantic is not the permanent fixture it appears to be. It is a passing phase in the life of the planet, and it may already carry the first faint seed of its own ending at a strait we can point to on a map. Which leaves us with two very different clocks ticking over the very same ocean, and the difference between them is the whole point. So the Atlantic is entering a new phase, but it turns out there are two of them, ticking on two wildly different clocks, and only one of them is ours to worry about. Bring the whole journey together. We began with a current. the great conveyor that carries warmth north and steadies the climate of a continent. We watch the warning signs gather. The cold blob in the wrong place. Greenland's ice melting into the engine. A history of sudden collapse 7 times over, including the deep freeze our own ancestors lived through. And a modern alarm suggesting the current may be on a tipping course right now. That is the fast clock. It moves on the scale of a human life. Decades. Maybe within your lifetime, maybe your children's, maybe further off, because the timing is genuinely uncertain and honest scientists disagree. But it is close enough to matter to real people alive today. If the conveyor slows or breaks, the sea climbs against American cities, Europe's seasons turn savage, the monsoons that feed billions waver, the rainforest strains and the fisheries thin. That is the serious question for America, and for the world. It is a question about our century, or the next. Then there is the slow clock. The Atlantic is a whole ocean, born from the breakup of Pangaea, growing for 180 million years, and perhaps tens of millions of years from now, beginning the long turn toward its own closing as a sleeping diving zone at Gibraltar wakes and invades. That is a change so vast and so distant that no person will ever witness it. It belongs to the planet's deep time, far beyond anything human. 2 phases, 2 clocks. One matters to the tide outside a house in Miami this century. The other matters to the shape of the world tens of millions of years from now. It would be easy to mix them up, to hear that the Atlantic is entering a new phase and feel a distant, harmless awe. The important thing is to keep them separate. The deep future is a wonder. The near future is a responsibility. Here is what ties both clocks together, and it is the quiet lesson under this whole story. The Atlantic is not the fixed, eternal thing it pretends to be. The steady ocean, the reliable current, the unchanging coastline, all of it is in motion. All of it is passing through phases. All of it is capable of change. We built our cities, our farms, and our whole idea of normal on top of a system that was always secretly in flux. That is a humbling thought, and also a useful one. It means the calm we take for granted was never guaranteed. It was granted by a current that happened to be strong, in a climate that happened to be steady, during a sliver of time that happened to suit us. Understanding that is the first step to protecting it, so the next time you stand on a beach and watch the Atlantic roll in, look a little differently at that endless, patient water. Beneath the calm surface, a current is straining. Across the deep floor, a drain is stirring. The most permanent thing on the planet is quietly on the move. And the only real question that belongs to us is a simple one. Now that we know the ocean can change, what will we choose to do while there is still time to choose at all?